We have a famous slide which will come on, which we'll do, which is the following slide. It characterizes the various versions of MapReduce and also uh, pleasingly parallel, which is a so-called map only, which is a special case of MapReduce. And so we have these um, actually 5 types of MapReduce now: pleasingly parallel, MapReduce, MapReduce stats, MapReduce, ITA, and HPC. So those are all variants of MapReduce with slightly different structure. In each case, they have an overall, the same thing which we've already discussed many times: single program, multiple data, divide the thing that's big up, and use lots of processes with each process running the same software, tackling part of the problem. And then this is all done over the particular data set with a particular form of parallelism. Then in each case, the calculation done is a map, and then the communication is the reduce. And in the case where there's effectively no reduction, is map only. The case of MapReduce has one set of maps followed by one set of reductions. MRStat I just put down because it's quite common, where the reductions are really simple, global averages, so they really take no time. At least say in the particle physics case, the global averages are very fast compared to the 10 seconds it takes to process an event. Um, we've mentioned that iterative MapReduce is an important concept because when you do so-called expectation maximization and parallel linear algebra, you always have multiple waves of maps followed by reductions because you're iterating. You do not have one map followed by one set of maps followed by one set of reductions. You have map, reduce, map, reduce, map, reduce, and you need to save the data in memory between the different stages. And then finally, the other class we have is high performance computing, which is single program, multiple data. But the communication is typically not reductions, it's point to point. And the messages tend to be quite small, and there's a lot of efficiency needed in programming and the hardware to be able to make message passing efficient for small messages. Here's this picture, shows PP is map only is A, MapReduce and MapReduce stat are the classic MapReduce. MapReduce ITA is C, and a high performance computing or MPI is D. And we have the structure illustrated here, just maps. We have maps followed by reductions, maps followed by reductions, and then we loop back after reductions, have a new set of maps, new reductions, and loop back again. And in the case of HPC, we have local point-to-point communications, not reductions. So we know the last set of discussion corresponds to the actual analytics used, which is this library, it's like Mahout for the Apache Big Data Stack. And so this is in the case of the title of the class, Application Analytics, this is the analytics. I noted there were 2 important styles of analytics, global and local, depending if the analytics is really focusing at each analytics goes on one point, or the analytics crosses all points. And with pleasingly parallel applications, we have this, like in the particle physics, you have a local computation, which is the really messy, takes 10 seconds for the average event from Atlas and CMS. If you do heavy ion collisions, it takes a lot longer, in fact. And so that's one case. When we go to iterative MapReduce, ego, and expectation maximization, those require global machine learning. And typically these are where non-trivial parallel algorithm work is done, and it can be challenging both for algorithms or implementations. We haven't really defined machine learning, and I'm not actually totally certain if everybody agrees exactly what machine learning is. The way it's used these days is almost anything is machine learning if it's an analysis. And but certainly clustering and is a machine learning, a typical machine learning algorithm. Um, Neural nets, machine learning networks, and machine learning, and so on. Now, if I look at these use cases, particle physics or the radar analyses 43 and 44, they have domain-specific analysis, which is called signal processing for radar data. It uses things like fast Fourier transforms, classic algorithms. You would not normally call that machine learning. Although more and more, some of these analyses are using local, like in astronomy, they're using local machine learning components. By local, I mean you apply it to each point, rather than, so they're using the local machine learning just in the actual processing of the raw data points as well as in the overall discovery process, which is the global example of machine learning. Because if you're doing discovery and across the whole data set, that's where you'd expect to need global machine learning, because you're integrating the global results from everything. And remember, in the particle physics example, that global step ended up as histogramming, which is really not machine learning. It's too simple to be called machine learning. I have this classification called expectation maximization. I didn't actually write that down for any of the use cases. Many of them use it. And the main reason I didn't do it is in most of the cases you can't actually tell whether they're using it. In some cases where they're using clustering, that uses expectation maximization. So it's I could have written it down, but in most cases I couldn't find out exactly what algorithms they were using. Anyway, it's a class of iterative approach to optimization where you you do tractable analyses by making approximations in 2 steps. You have an iterative algorithm, you fix some of the variables at the values of at the previous iteration, find the values of the next iteration for other variables, and then you, in the maximization step, you find the remaining variables, and then you iterate this approximately, because you can't find an exact optimization. So you do it iteratively by fixing and minimizing some of the subset. We already pointed out that the graph classification is important because there's a processing graphs is particularly tricky. A lot of the methods used for non-graph algorithms don't work very well because they have very irregular, difficult to predict structure, and that makes the whole calculation much harder. Collaborative filtering is possibly one of the most important algorithms ever invented. Remarkable how successful that is when used in Netflix and Amazon and places like that. And it's an approach for matching interests of one user with other users and tell you what data you're meant to investigate. And as we'll see when we study it, there are 3 subclasses: user-based, item-based, and content-based, and then some hybrid combination of them. So that's the end. So we've been through giving you a short discussion of all the things we use to classify those use cases, to tell you, and the idea is to point out what things you need to put together and how they vary from case to case. And it maybe will help other people to classify further use cases, see what new cases are not captured in those 51, what features, and so on. Thank you very much, and I apologize for being me on all these slides. Thank you.